Tonight, we are going to meet the most terrifying objects in the universe. Not black holes, something stranger, something that should not exist according to the physics we learned in school. Objects so dense that a single teaspoon of their material weighs 6 billion tons, more than every car, truck, ship, and building on Earth combined. Objects that spin hundreds of times per second, sweeping beams of radiation across the cosmos like lighthouses from hell. Objects whose magnetic fields are so powerful that they could erase every credit card on Earth from halfway across the solar system, and rip the iron from your blood if you got within 1,000 kilometers. Neutron stars. And here is what makes them truly terrifying. When two of these objects collide, they do not merely produce an explosion. They produce a kilonova, a cataclysm so violent that it outshines an entire galaxy for a brief blinding moment and forges the heaviest elements in the periodic table. The gold in your wedding ring, the platinum in your watch, the uranium in nuclear reactors. All of it, every atom of every heavy element on Earth was created in the collision of neutron stars billions of years ago, scattered across space by an explosion so powerful that it sent ripples through the fabric of space-time itself. In 2017, we detected those ripples for the first time. Gravitational waves from two neutron stars spiraling into each other 130 million light-years away. It was the most observed astronomical event in human history. Over 70 observatories on every continent and in space turned to watch. And what they saw changed everything we thought we knew about where the elements come from, how gravity works, and what happens when matter is pushed beyond every known limit. Tonight we are going to walk through 7 shocking discoveries about neutron stars. Discoveries that have forced physicists to confront the most extreme conditions in the universe and question the very foundations of nuclear physics. We will go inside the heart of a dying star. We will watch the birth of a neutron star in the core of a supernova. We will meet magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, capable of producing flares so energetic that one, in 2004, briefly disrupted Earth's atmosphere from 50,000 light-years away. We will follow the story of Jocelyn Bell Burnell, the graduate student who discovered pulsars and was denied the Nobel Prize. We will journey to the interior of a neutron star, where matter exists in forms so exotic that they have names like nuclear pasta. And we will witness the collision of 2 neutron stars, the cosmic forge that created every heavy element in your body. By the end of tonight, you are going to understand why neutron stars are the most extreme, most violent, and most important objects in the cosmos, and why the gold in the ground beneath your feet is a message from the death of stars. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand neutron stars, we first need to understand how stars die. Because a neutron star is not born, it is forged in the most violent event the universe has to offer. Every star is a balance, a negotiation between 2 forces that have been locked in opposition since the star ignited. On one side, gravity, the relentless inward pull of the star's own mass, trying to crush everything into a single point. On the other side, radiation pressure, the outward push generated by nuclear fusion in the star's core, where hydrogen atoms are squeezed together so tightly that they fuse into helium, releasing energy in the process. For most of a star's life, these 2 forces are in equilibrium. Gravity pulls in, fusion pushes out. The star holds steady, burning through its hydrogen fuel at a rate that depends on its mass. Small stars, red dwarfs, the most common type of star in the galaxy, burn slowly and efficiently, sipping their hydrogen over tens of billions of years. Some of them will still be shining long after the sun has died. Our sun, a medium-sized yellow dwarf, has enough hydrogen for about 10 billion years. It is roughly halfway through its main sequence lifetime right now. But massive stars, stars 8 or more times the mass of the sun, burn through their fuel far more quickly. They are the giants of the galaxy. The blue supergiants, the hypergiants, the luminous blue variables. Stars like Rigel in the constellation Orion, which shines 120,000 times brighter than the sun. Stars like Eta Carinae, which is so massive and so unstable that it has already thrown off enormous eruptions of material and may go supernova within the next few 100,000 years. The most massive stars live only a few million years, a blink of an eye on cosmic timescales. They burn fast, burn bright, and die young. And when they die, they do not go quietly. When a star exhausts its hydrogen, the balance shifts. The core, no longer producing energy through hydrogen fusion, begins to contract under gravity. As it contracts, it heats up, and eventually becomes hot and dense enough to fuse helium into carbon and oxygen. A new source of energy, a new outward push. The balance is restored, but only temporarily. For massive stars, this process repeats. Carbon fuses into neon. Neon fuses into oxygen. Oxygen fuses into silicon. Each new fuel ignites at a higher temperature, burns faster, and produces heavier elements. The star develops an onion-like structure, concentric shells of different elements, each one fusing at a different rate, each one burning hotter and faster than the last. The final stage is silicon fusion, and this stage is breathtakingly brief. Silicon fuses into iron in the star's innermost core, a process that takes only a single day, one day. After millions of years of hydrogen burning, hundreds of thousands of years of helium burning, 600 years of carbon burning, 6 months of neon burning, a year of oxygen burning, silicon burns through in 24 hours. The star, which has spent its entire existence in measured, steady fusion, suddenly races through its final fuel supply in less time than it takes the Earth to rotate once. And this is where the story takes a dark turn, because iron is the end of the line. Iron is the most tightly bound nucleus in nature, iron 56 to be precise, with 26 protons and 30 neutrons, locked together in the most stable configuration that nuclear physics allows. Fusing iron does not release energy, it absorbs energy. Every element before iron gave the star something: energy, outward pressure, a reason to keep shining. Iron takes, it is an energy sink, a dead end, a trap. When the core fills with iron, roughly 1.5 times the mass of the sun, compressed into a sphere the size of Earth, fusion stops. The outward pressure vanishes, and in that instant, in a fraction of a second, gravity wins. What happens next is almost beyond comprehension. The Iran core, now about 1.5 times the mass of the sun, collapses. Not slowly, not gradually. It collapses at 1/4 of the speed of light. In less than a second, a ball of iron the size of Earth is crushed to a sphere roughly 20 kilometers across, about the size of a city. The density increases by a factor of 100 billion. The temperature soars to over 100 billion degrees. During this collapse, the electrons and protons in the iron atoms are squeezed together so violently that they merge, a process called electron capture or inverse beta decay. Each proton absorbs an electron and becomes a neutron, releasing a neutrino in the process. The entire core converts from iron to neutrons in milliseconds. Trillions upon trillions of neutrinos flood outward, carrying away an almost inconceivable amount of energy. In those few seconds, the collapsing core releases more energy in neutrinos alone than the Sun will produce in its entire 10 billion year lifetime. The core, now made almost entirely of neutrons, reaches nuclear density, approximately 230 million tons per cubic centimeter. At this density, the neutrons resist further compression through a quantum mechanical effect called neutron degeneracy pressure, the same principle that prevents two neutrons from occupying the same quantum state. The collapse halts, the core bounces. That bounce sends a shock wave outward through the still-in-falling outer layers of the star. But the shock wave alone is not enough. As it plows into the dense, still-falling material above the core, it stalls, losing energy to the dissociation of ion nuclei that it crashes through. For a brief, critical period, perhaps 100 milliseconds, the shock wave hangs in the balance, neither advancing nor retreating. If nothing revives it, the entire star collapses into a black hole. No neutron star, no supernova, just silence. What saves it is the neutrinos. The flood of neutrinos pouring outward from the newly formed neutron core is so intense that even though neutrinos barely interact with matter, a single neutrino can pass through a light year of solid lid without being absorbed. The sheer number of them passing through the dense material behind the stalled shock wave deposits enough energy to revive the blast. The shock wave is re-energized, it surges outward, and the star is torn apart. We have indirect proof of this neutrino-driven mechanisms. On February 23, 1987, a supernova appeared in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, about 168,000 light-years away. It was the closest supernova observed since Kepler's supernova of 1604, and the first to be detected by modern instruments. About 3 hours before the visible light from the explosion reached Earth, two neutrino detectors, Kamiokan Deathkid in Japan and the IMB detector in the United States, registered a burst of neutrinos, 24 neutrinos in total, arriving over a span of about 13 seconds. 24 particles out of the roughly 10 to the power of 58 that the supernova produced, intercepted by instruments on a tiny planet 168,000 light-years away. Those 24 neutrinos confirmed the core collapse model of supernovae, proving that the energy of the explosion was carried primarily by neutrinos, not by light or shock waves, exactly as the theory predicted. The detection of neutrinos from SN 1987A was awarded the 2002 Nobel Prize in Physics. The outer layers of the star are blasted into space at speeds of up to 30,000 kilometers per second, about 10% of the speed of light. This is a core collapse supernova, one of the most energetic events in the universe, briefly outshining an entire galaxy of hundreds of billions of stars. For a few weeks, a single dying star produces more light than the combined output of hundreds of billions of living ones. And at the center of the expanding debris cloud, where the star used to be, sits the newborn neutron star, a ball of neutrons 20 kilometers across, with a mass between 1.5 and about 2.25 times the mass of the Sun. It is the densest object in the universe that has a surface denser than anything except a black hole, which has no surface at all. Not every massive star produces a neutron star. If the collapsing core is too massive, above about 2 to 2.5 solar masses, a limit we will return to later in our story, not even neutron degeneracy pressure can halt the collapse. The core does not bounce. It falls through the neutron star stage entirely and collapses directly into a black hole. The division between these two outcomes, neutron star or black hole, depends on the mass of the progenitor star. Stars between about 8 and 25 solar masses generally produce neutron stars. Stars above about 25 solar masses generally produce black holes, but the boundaries are fuzzy, complicated by factors like metallicity, rotation, magnetic fields, and whether the star is in a binary system. Nature does not draw clean lines between outcomes. It paints in broad, overlapping strokes. For the stars that do produce neutron stars, the result is an object that defies everyday intuition. Let us pause here and try to comprehend what we are dealing with. A neutron star is roughly 20 kilometers in diameter. That is about the length of Manhattan Island. If you could somehow place a neutron star where New York City is, it would fit comfortably between Midtown and the financial district. But it would contain more mass than the Sun, a sphere of hot plasma 1.4 million kilometers across, compressed into a space you could drive across in 15 minutes. The density is staggering. A cubic centimeter of neutron star material, a piece the size of a sugar cube, weighs approximately 400 million tons. A teaspoon weighs about 6 billion tons. If you dropped a teaspoon of neutron star material onto the surface of the Earth, it would not simply sit there. It would punch through the crust like a bullet through tissue paper, burrowing toward the center of the planet under its own colossal weight. The surface gravity of a neutron star is about 200 billion times the surface gravity of Earth. If you could somehow stand on the surface, which you could not because you would be instantly crushed into a film of atoms, you would weigh about 30 trillion kilograms. A marshmallow dropped onto a neutron star would hit the surface with the energy of a nuclear bomb. The escape velocity, the speed needed to leave the surface, is about 100,000 kilometers per second. That is 1/3 the speed of light. Even light itself is bent by the gravitational field. A neutron star is so compact that you could see parts of the back of the star while looking at the front, because the gravity curves the light around the surface. The surface temperature of a young neutron star is about 600,000 degrees Kelvin, hot enough to glow in X-rays. Over millions of years, the star cools, but the surface remains extraordinarily hot by terrestrial standards. And that surface is not smooth. It is a landscape, if you can call it that, of solidified iron nuclei arranged in a crystalline lattice topped by an atmosphere so thin that it measures in millimeters, composed mainly of hydrogen or helium so hot that it emits X-ray photons. Occasionally, the surface erupts. If the neutron star is accreting material from a companion star, hydrogen and helium accumulate on the surface in a thin layer. When the layer reaches a critical temperature and density, compressed by the enormous surface gravity, it ignites in a thermonuclear explosion, a type 1 X-ray burst. The entire surface of the neutron star, all 300 or so square kilometers of it, is engulfed in a thermonuclear firestorm in less than a second. The burst releases as much energy in 10 seconds as the sun emits in a full week. These bursts repeat, sometimes hours apart, sometimes days, as new material accumulates and ignites. They are so energetic that they can be detected by X-ray telescopes from halfway across the galaxy. And they are so well understood theoretically that they can be used as standard candles, calibrated explosions whose known energy output allows astronomers to estimate the distance to the neutron star. Some X-ray bursts are even more dramatic. In rare cases, the nuclear fire is so intense that it produces heavier elements, carbon in particular, that ignite in a secondary explosion deep within the accumulated layer. These superbursts are 1,000 times more energetic than ordinary X-ray bursts and can last for hours. They are thought to burn through the entire accumulated carbon layer on the neutron star's surface, resetting the clock for the next superburst, which may not occur for years. And they spin. Dear God, they spin. When the core of the massive star collapses from the size of Earth to the size of a city, conservation of angular momentum causes it to spin up dramatically. The same effect that makes a figure skater spin faster when she pulls her arms in. A star that was rotating once every few days before collapse becomes a neutron star rotating many times per second. Some neutron stars spin so fast that their surfaces move at a significant fraction of the speed of light. The fastest known spinning neutron star is a pulsar called PSR J1748-2446 located in a globular cluster about 18,000 light-years away. It rotates 716 times per second. 716. Its surface at the equator is moving at about 24% of the speed of light, roughly 70,000 kilometers per second. If Earth rotated that fast, the surface at the equator would be moving so quickly that anything not bolted to bedrock would be flung into space. The neutron star holds together only because its gravity is so immense that not even these extraordinary rotational forces can tear it apart. Now, let us talk about what is inside a neutron star. Because the interior is where physics goes from extreme to genuinely bizarre. This is shocking discovery number 1. The impossible interior. The surface of a neutron star is a crust, a thin, rigid layer of crystallized ion nuclei and free electrons, perhaps a kilometer or 2 thick. This crust is the hardest material in the universe, about 10 billion times stronger than steel. It can support mountains, irregularities in the surface, but these mountains are at most a few centimeters tall. On a neutron star, even a millimeter-high bump requires more structural strength than any material on Earth could provide. Beneath the crust, things get stranger. As you move deeper, passing from densities of about 100 million tons per cubic centimeter at the base of the crust to billions of tons per cubic centimeter in the outer core, the matter undergoes a series of phase transitions that have no analog in our everyday experience. On Earth, we are familiar with phase transitions. Ice melts into water, water boils into steam. These transitions involve the rearrangement of molecules. Inside a neutron star, the phase transitions involve the rearrangement of atomic nuclei themselves. The nuclei, packed closer and closer together by the increasing pressure, begin to deform. They lose their spherical shapes. They stretch into elongated shapes. They flatten into sheets. They form tubes and bubbles and interconnected networks. These exotic configurations have been given names by physicists who, despite working with the most extreme physics in the universe, apparently have a sense of humor. They call it nuclear pasta. The names come from the shapes. At relatively low densities, just below the crust, the nuclei elongate into cylindrical shapes. These are called spaghetti. At higher densities, the cylinders flatten into sheets, lasagna. Deeper still, the sheets develop holes, Swiss cheese or anti-spaghetti. And at even greater densities, the matter transitions into a uniform sea of neutrons with occasional bubbles of empty space, anti-lasagna. Nuclear pasta is not a joke. Despite the names, it is one of the strongest materials theoretically possible. Perhaps 10 billion times stronger than steel, capable of supporting the enormous stresses inside a neutron star, and it may have observable consequences. The breaking of nuclear pasta layers, when the stresses exceed even their enormous strength, may be responsible for a phenomenon called a starquake, a sudden cracking of the neutron star's interior structure that releases enormous amounts of energy and causes a detectable glitch in the star's rotation. Below the pasta layers, in the outer core, matter exists as a sea of neutrons with a small fraction of protons and electrons. This material is thought to behave as a superfluid, a quantum state of matter with zero viscosity capable of flowing without friction. In a neutron star, this means the neutrons in the outer core can form vortices, tiny whirlpools of circulating superfluid that are responsible for storing the star's angular momentum. When the crust slows down due to electromagnetic braking, the superfluid interior may not slow down at the same rate. Angular momentum is stored in the vortex lines. Periodically, these vortices unpin from the crust and transfer their angular momentum suddenly, causing the star to spin up briefly, a glitch. The Vela pulsar, one of the best studied pulsars in the sky, has experienced dozens of such glitches, each one a window into the superfluid interior that would otherwise be completely invisible. And at the very center of the neutron star, the inner core, nobody knows what exists. The density exceeds that of an atomic nucleus by a factor of 2 to 5. At these densities, the neutrons themselves may break apart. Neutrons are not fundamental particles. They are made of free quarks, bound together by the strong nuclear force. At sufficient densities, the quarks may become deconfined, freed from their neutron prisons, and forming a new state of matter called quark matter or a quark gluon plasma. This state of matter has not been directly observed inside a neutron star. It existed briefly after the Big Bang, when the universe was a fraction of a second old and the temperatures were trillions of degrees. If it exists inside neutron stars today, these objects would contain a core of matter in a state that has not existed freely in the universe for nearly 14 billion years. There is another possibility, even more exotic. Some theorists have proposed that the quarks inside the core might rearrange themselves into strange matter, a mixture of up, down, and strange quarks that could be more stable than ordinary nuclear matter. If this is true, then the entire neutron star might eventually convert to strange matter, becoming a strange star, an object made entirely of a material that does not exist anywhere else in the observable universe. The equation of state of neutron star matter, the relationship between pressure and density inside these objects, is one of the most important unsolved problems in physics. It connects nuclear physics, particle physics, and astrophysics in a way that no laboratory experiment on Earth can replicate. We cannot create the pressures and densities found inside neutron stars in any terrestrial facility. The only laboratories are the neutron stars themselves, and reading the data requires observing them from thousands of light years away. NASA's NICER instrument, the Neutron Star Interior Composition Explorer, mounted on the International Space Station, has been doing exactly that since 2017. By measuring the precise shapes of X-ray pulses from rotating neutron stars, NICER can determine the star's radius to within a few hundred meters. Combined with mass measurements from other methods, these radius measurements constrain the equation of state, telling us how stiff or soft the material inside the star really is. The results have been remarkable. NICER has measured the radii of several neutron stars with unprecedented precision, finding that they are typically between 11 and 13 kilometers, smaller than many cities, yet containing more mass than the Sun. These measurements have ruled out some proposed equations of state and supported others, narrowing the range of possibilities for what exists inside the core. But the definitive answer, whether quark matter, strange matter, or something else entirely, remains beyond our current reach. We are, in a very real sense, trying to understand the nature of matter itself by studying objects that are thousands of light years away, invisible to the naked eye, and governed by physics at the very edge of what our theories can describe. It is one of the great intellectual challenges of our time, and one of the most humbling. The interior of a neutron star is one of the few places in the universe where all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are simultaneously important. It is a place where general relativity meets quantum mechanics, where nuclear physics meets astrophysics, where the science of the very large meets the science of the very small. Understanding what is inside a neutron star may require a theory that unifies these different branches of physics, a theory that, despite decades of effort, we do not yet possess. In a sense, every neutron star is a message from nature, a message that says, your physics is incomplete. Come back when you have better tools and deeper understanding. We are waiting. This is shocking discovery number 2. The cosmic lighthouses. In November 1937, a 24-year-old graduate student at the University of Cambridge was reviewing data from a radio telescope she had helped build, stringing over 57 acres of wire and posts across a muddy field in the English countryside. Her name was Jocelyn Bell, and she was looking for quasars, distant, powerful radio sources that twinkled as their signals passed through the solar wind. What she found instead was something no one had ever seen before. In the data recorded on hundreds of feet of paper chart, Bell noticed a strange signal, a series of pulses spaced exactly 1.337 seconds apart, repeating with a regularity that seemed almost artificial. The signal was too fast to be a star, too regular to be random noise, too precise to be natural. Bell and her thesis supervisor, Anthony Hewish, initially had no explanation. They considered, half seriously, half as a dark joke, the possibility that the signal was artificial. They called it LGM-1, Little Green Men. For a few weeks, the most extraordinary explanation seemed almost as plausible as any natural one. Were they receiving a signal from an extraterrestrial civilization? Then Bell found a second pulsing source in a completely different part of the sky, and then a third, and a fourth. The chances of multiple alien civilizations, all sending signals with similar characteristics, were essentially zero. These had to be natural objects, but natural objects unlike anything astronomers had ever encountered. The objects were pulsars, rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. As the neutron star rotates, the beams sweep across the sky like the beams of a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a pulse of radio emission each time the beam sweeps past, once per rotation. The extraordinary regularity of the pulses, stable to parts per billion in some cases, reflects the extraordinary stability of the neutron star's rotation. But why do the beams come from the magnetic poles? The answer lies in the structure of the neutron star's magnetosphere, the region of space surrounding the star where the magnetic field dominates the behavior of charged particles. As the neutron star rotates, its powerful magnetic field sweeps through the surrounding space, accelerating electrons and positrons to near the speed of light along the magnetic field lines. These accelerated particles emit radiation, primarily in the radio wavelengths, but also in optical, X-ray, and even gamma-ray frequencies, depending on the energy involved. The emission is concentrated near the magnetic poles, where the field lines converge and the particle acceleration is most intense. Because the magnetic axis of a neutron star is typically not aligned with its rotation axis, just as Earth's magnetic poles are not exactly at the geographic poles, the beams sweep around as the star rotates, creating the pulsed signal that we detect. The mechanism that actually produces the radio emission is, remarkably, still not fully understood, even after more than 50 years of study. We know that the radiation is coherent, meaning the particles are radiating in concert rather than independently, which produces emission far more powerful than any individual particle could produce alone. Several models have been proposed: curvature radiation, synchrotron maser emission, and others. But no single model explains all the observational properties of all pulsars. It is one of the enduring puzzles of neutron star physics. We can detect these objects from across the galaxy. We can time their pulses to nanosecond precision. And yet we do not fully understand the basic physical process that produces the radiation we observe. The discovery of pulsars was one of the most important astronomical discoveries of the 20th century. It confirmed the existence of neutron stars, objects that had been predicted theoretically by Walter Baade and Fritz Zwicky in 1934, more than 30 years earlier, but had never been directly observed. Baade and Zwicky had published a remarkable paper at the meeting of the American Physical Society at Stanford, in which they proposed two ideas that were both considered outrageous at the time. First, that ordinary stars could explode with extraordinary violence, releasing as much energy in a few days as the sun emits in 1 billion years, events they named supernovae. And second, that the core of such an exploding star might collapse to a state of incredible density, forming a neutron star, a star made almost entirely of neutrons, packed together at nuclear density, only 2 years after the neutron itself was discovered by James Chadwick. The prediction was regarded as highly speculative. Most physicists doubted that such extreme objects could actually exist. The idea lingered in the theoretical literature for decades, an elegant curiosity that most astronomers filed under probably impossible. Bell's discovery proved them spectacularly wrong. Pulsars were neutron stars. The theory was real, and the universe was stranger than almost anyone had imagined. What followed was one of the most productive periods in the history of astrophysics. Within months of Bell's discovery, astronomers found pulsars inside supernova remnants, confirming the Baade-Zwicky connection between supernovae and neutron stars. They found pulsars that were slowing down, confirming that the rotation was the energy source. They found pulsars in binary systems, orbiting companion stars, which opened the door to measuring neutron star masses with exquisite precision. And in 1992, a pulsar provided perhaps the most surprising discovery of all: the first confirmed exoplanets. The planets of PSRB Jouln 57 plus Jouln were the first planets ever discovered outside our solar system, and they orbited a dead star, 2 Earth-mass planets and 1 Moon-mass planet circling a millisecond pulsar in the constellation Virgo. The discovery was made by Alexander Wolszczan and Dal Freyel, who detected tiny periodic variations in the pulsar's timing, shifts of just a few millionths of a second caused by the gravitational tug of unseen planets. The irony was profound. The first worlds we found beyond our own solar system were orbiting not a living star, but a remnant of a catastrophic stellar death. These planets could not have survived the supernova that created the pulsar. They must have formed afterward, coalescing from the debris disk left behind by the explosion. They are second-generation worlds, born from the ashes of a dead star, orbiting a lighthouse made of nuclear matter in the perpetual darkness between the stars. There is a human story threaded through this scientific triumph, and it deserves to be told. The 1974 Nobel Prize in Physics was awarded for the discovery of pulsars. It went to Anthony Hewish, Bell's thesis supervisor, and Martin Ryle, the head of the radio astronomy group. Jocelyn Bell was not included. The omission has been widely regarded as one of the greatest injustices in the history of the Nobel Prize. Bell herself has been characteristically gracious about it, noting that she was a graduate student at the time and that Nobel Prizes are traditionally awarded to senior scientists. But the astronomical community has never forgotten. In 2018, Bell was awarded the Special Breakthrough Prize in Physics, worth $3 million, which she donated entirely to fund scholarships for women and minority students in physics. The gesture was typical of a scientist who changed our understanding of the universe and asked for nothing in return. Pulsars have also found their way into one of humanity's most ambitious messages to the cosmos. When NASA launched the Voyager spacecraft in 1977, each probe carried a golden record, a phonograph record containing sounds and images of Earth, intended as a message to any extraterrestrial civilization that might one day encounter it. On the cover of each record is an engraved diagram showing the position of the Sun relative to 14 known pulsars. Each pulsar identified by its unique rotational period encoded in binary. The idea, proposed by astronomer Frank Drake, was that any civilization advanced enough to find the Voyager probes would likely know about pulsars and could use the diagram to determine exactly where in the galaxy the spacecraft came from and when it was launched. Pulsars, with their unique timing signatures, serve as cosmic street addresses, landmarks that are recognizable from anywhere in the galaxy. Since Bell's discovery, more than 3,000 pulsars have been found. They come in a dazzling variety. Normal pulsars rotate between about 1 and 30 times per second, slowing down gradually over millions of years as they lose rotational energy through electromagnetic radiation. Their spin-down rate is remarkably steady, so steady that pulsars are among the most accurate clocks in the universe, rivaling the best atomic clocks on Earth. Millisecond pulsars are old pulsars that have been recycled, spun back up to extraordinary speeds by accreting matter from a companion star. As gas from the companion falls onto the neutron star, it transfers angular momentum, spinning the neutron star up to rotational periods of just a few milliseconds, hundreds of rotations per second. The fastest of these, PSR J1748 Dev 446 odd, spins 716 times per second. These millisecond pulsars are the most stable clocks known. Their timing stability over years rivals that of the best cesium atomic clocks, making them useful for a variety of precision experiments, including the detection of gravitational waves through pulsar timing arrays. And then there are the spider pulsars, a particularly dramatic class that has earned its name from the way these objects treat their companions. Black widow pulsars are millisecond pulsars that are slowly destroying their companion stars. The intense radiation and particle wind from the pulsar bombards the companion, stripping away its outer layers and gradually evaporating it, like a black widow spider consuming its mate. Redback pulsars are similar but have more massive companions that fight back, switching between states of active accretion and radio pulsar behavior. These systems are violent, dynamic, and provide some of the best laboratories for studying the interaction between neutron star radiation and stellar matter. There is a pulsar at the heart of the Crab Nebula, one of the most famous objects in the sky that connects these cosmic lighthouses to human history in a remarkable way. On July 4th, 1054 AD, Chinese astronomers recorded the appearance of a guest star in the constellation we now call Taurus. The star was so bright that it was visible in daylight for 23 days and remained visible to the naked eye at night for nearly 2 years. What they witnessed was a supernova, the explosive death of a massive star approximately 6,500 light-years from Earth. The expanding debris cloud from that explosion is what we now call the Crab Nebula, a glowing, tangled web of gas and filaments about 11 light-years across, still expanding at about 1,500 kilometers per second, nearly 1,000 years after the explosion. And at the very center of the nebula, hidden inside the tangled wreckage, is the Crab pulsar, a neutron star rotating about 30 times per second, emitting beams of radiation from radio waves to gamma rays. The Crab pulsar is the engine that powers the entire nebula. Its rotational energy, slowly bleeding away, drives the magnetic field and the particle wind that make the nebula glow. It is losing energy at a prodigious rate. Its rotation is slowing down by about 38 nanoseconds per day, and that energy has to go somewhere. It goes into the nebula, illuminating it from within, making it one of the brightest and best studied objects in the sky. The Crab pulsar was one of the first pulsars discovered after Bell's initial detection, and it provided the clinching evidence that pulsars were indeed rotating neutron stars. Its location at the exact center of a known supernova remnant, a remnant whose creation had been witnessed and recorded by human beings nearly 1,000 years earlier, made the connection between supernovae and neutron stars undeniable. The guest star that Chinese astronomers had marveled at in 1054 had left behind one of the most extraordinary objects in the galaxy, a lighthouse made of nuclear matter spinning in the wreckage of its own birth, visible across the electromagnetic spectrum from Earth. There is something poignant about this connection across time. A Chinese court astronomer, standing in the pre-dawn darkness of a July morning in 1054, looked up and saw a new star, where no star had been before, bright enough to read by, bright enough to cast shadows. He recorded it on silk, in brush and ink, as was the custom. He could not have known what he was witnessing: the death of a star 8 times more massive than the Sun, collapsing and exploding across 6,500 light-years of space, the light from that catastrophe finally reaching Earth after a journey that began before the first pyramids were built. He could not have known that the explosion would leave behind a spinning ball of neutrons that would still be pulsing, still be radiating, still be powering its nebula 1,000 years later. He just saw a guest star, and he wrote it down. And because he wrote it down, we know exactly when and how the Crab pulsar was born. A direct connection between a medieval observation and a modern understanding of the most extreme physics in the universe. This is shocking discovery number 3. The strongest magnets in the universe. In the catalogue of extreme objects, magnetars occupy a special place. They are neutron stars, but neutron stars with magnetic fields so powerful that they beggar the imagination. A typical refrigerator magnet produces a magnetic field of about 5 millitsla. An MRI machine, which uses powerful superconducting magnets to image the inside of your body, produces a field of about 1.5 to 3 Tesla. tens of thousands of times stronger than a refrigerator magnet. The strongest continuous magnetic field ever produced in a laboratory is about 45 Tesla. A magnetar's magnetic field is about 10 to the power of 11 Tesla. That is 100 billion Tesla. A quadrillion times stronger than Earth's magnetic field. A billion times stronger than the strongest laboratory magnet. It is, by a spectacular margin, the most powerful magnetic field known to exist in the universe. At this field strength, the familiar rules of physics begin to break down. Atoms are distorted into elongated shapes, stretched along the magnetic field lines into thin cylinders. The vacuum of space itself becomes birefringent. It develops different optical properties in different directions, splitting light into two beams like a crystal of calcite. Even the structure of matter changes. The electron orbitals around atoms are compressed into one dimension, creating exotic magnetic atoms with properties unlike anything found on Earth. If a magnetar were located at the distance of the Moon, about 380,000 kilometers away, its magnetic field would be strong enough to erase every credit card on Earth, wipe every hard drive, and disrupt every electronic device on the planet. If you were within about 1,000 kilometers of a magnetar, the magnetic field would be strong enough to distort the electron clouds around the atoms in your body, tearing apart chemical bonds and essentially disassembling you at the molecular level. You would not be crushed or burned. You would be atomized, your body literally pulled apart, bond by the sheer force of the magnetic field. To put the magnetic field's strength in perspective, consider this. The magnetic field of the Earth, which deflects solar wind particles and makes compass needles point north, is about 50 microtesla, 50 millionths of a Tesla. The magnetic field of a typical neutron star is about 100 million Tesla, already extraordinary, 1 trillion times stronger than Earth's. But a magnetar's field is another 1,000 to 10,000 times stronger than that. We are dealing with a hierarchy of extremes. Earth, ordinary magnets, MRI machines, laboratory record holders, ordinary neutron stars, and then, in a class entirely their own, magnetars. Each step is a leap of many orders of magnitude, and magnetars sit at the top of that ladder, utterly alone. These fields are not static. They evolve over time, and they do not evolve gently. A magnetar's magnetic field decays on time scales of about 10,000 years, fast by astronomical standards. As the field decays, it heats the neutron star's crust and interior, keeping the star much hotter than an ordinary neutron star of the same age. This internal heating is what powers the persistent X-ray emission that first drew astronomers' attention to magnetars. They were originally catalogued as anomalous X-ray pulsars, or AXPs, because their X-ray luminosity was far too high to be explained by rotational energy loss alone. Something else was powering them. That something was the decay of their enormous magnetic fields, the gradual unwinding of a quadrillion Tesla spring, releasing stored magnetic energy as heat over thousands of years. We know of roughly 30 confirmed magnetars in our galaxy. They are rare. Most neutron stars are not magnetars. The origin of their extreme magnetic fields is still debated, but the leading theory involves a dynamo mechanism during the first few seconds of the neutron star's life. In the immediate aftermath of the supernova, the newborn neutron star is incredibly hot and turbulent. Convection currents of superfluid neutrons churn through the interior at enormous speeds. If the neutron star is spinning rapidly enough during this brief convective phase, the combination of rotation and convection can amplify the magnetic field by a factor of 1,000 or more, producing the extreme fields we observe. The window for this amplification is brief, perhaps 10 to 30 seconds after the star's birth, and the conditions must be just right. This may explain why magnetars are rare. Most neutron stars are born spinning too slowly or with convection that is too weak to trigger the dynamo. Magnetars are also short-lived, at least by neutron star standards, because their enormous magnetic fields decay relatively quickly, dissipating their energy as heat and radiation over about 10,000 years. Magnetars are transient objects. After 10,000 years or so, the magnetic field has decayed to levels comparable to ordinary neutron stars, and the magnetar behavior, the bursts, the flares, the anomalous X-ray emission ceases. The object does not disappear, of course. It is still a neutron star. But it is no longer a magnetar. It has settled into a quiet retirement, its wild youth spent, its extraordinary magnetic energy radiated away into the cosmos. This means that every magnetar we observe today is young, born within the last few thousand to 10,000 years. The 30 or so magnetars we know of represent only the currently active population. Over the lifetime of the galaxy, millions of magnetars have been born, flared, and faded into ordinary obscurity. Magnetars announce their presence in the most dramatic way possible, through bursts and flares of extraordinary energy. On December 87th, 1830, a magnetar called SGR B500, located about 50,000 light-years from Earth, on the far side of our galaxy, produced the most energetic event ever observed from within the Milky Way. In 0.2 of a second, this magnetar released more energy than our Sun produces in 250,000 years. The burst was so intense that it briefly ionized Earth's upper atmosphere, affecting the ionosphere from 50,000 light-years away. It saturated the detectors on every X-ray and gamma-ray satellite in orbit. Had it occurred within 10 light-years of Earth, which, for the record, it did not, the gamma radiation would have been powerful enough to strip the ozone layer and sterilize the side of the planet facing it. The flare from SGR 1860 is thought to have been caused by a massive fracture in the magnetar's crust, a starquake of almost unimaginable violence. The enormous magnetic stresses inside the star built up over time, straining the crust until it cracked. When it broke, the magnetic field reconfigured catastrophically, releasing stored energy in a fraction of a second. The process is analogous to an earthquake on Earth, but on a neutron star, the energy scale is billions of times greater. Magnetars experience smaller bursts much more frequently. These soft gamma repeaters, named before their connection to magnetars was understood, produce irregular bursts of X-rays and gamma rays as the magnetic field twists, stresses, and occasionally ruptures the crust. Each burst is a window into the internal dynamics of the magnetar, the interplay between the ultra-strong magnetic field and the ultra-dense matter that contains it. And in April 2020, a magnetar called SGR did something that connected two of the biggest mysteries in modern astrophysics. It produced a fast radio burst, a brief, intense pulse of radio waves simultaneously with an X-ray burst. Fast radio bursts, or FRBs, are one of the most puzzling phenomena in astronomy. They are millisecond duration pulses of radio emission that appear to originate from distant galaxies billions of light-years away. Since their discovery in 2007, hundreds have been detected, but their origin has remained controversial. Were they caused by merging neutron stars, collapsing magnetars, something entirely new? The burst from SGR Ni-9035 plus Ni-15Ts, Uj-5Ts, detected simultaneously by the CHIME and STARE-2 radio telescopes in Canada and the United States, provided the first direct evidence that at least some fast radio bursts are produced by magnetars. The radio burst was less luminous than the extragalactic FRBs, about 1,000 times fainter, but it was unmistakably associated with a known magnetar in our own galaxy. If the same mechanism operates at higher energies in more extreme magnetars or in more violent environments, it could explain the distant FRBs that have puzzled astronomers for nearly 2 decades. The connection between magnetars and fast radio bursts has opened a new chapter in our understanding of these extreme objects. Magnetars are not just interesting curiosities, they may be responsible for one of the most widespread and mysterious signals in the cosmos. Every millisecond, somewhere in the universe, a fast radio burst flashes, a signal brighter than entire galaxies, lasting less time than the blink of an eye. And at least some of those signals may be coming from magnetars, neutron stars with magnetic fields so powerful that they can, in a fraction of a second, produce a signal detectable from billions of light years away. This is shocking discovery number 4. The cosmic forge. Everything you can touch, taste, see, or smell is made of atoms. And those atoms were made inside stars. Hydrogen and helium were forged in the Big Bang. Carbon, nitrogen, oxygen, silicon, iron, these were built in the nuclear furnaces of massive stars and scattered across space when those stars exploded as supernovae. This much has been known for decades. It is the foundation of our understanding of cosmic chemistry. But there was always a problem. The periodic table does not end at iron. There are elements heavier than iron: gold, platinum, uranium, thorium, lead, iodine, barium, and dozens more. These elements cannot be made by the normal fusion process inside stars, because fusing elements heavier than iron absorbs energy rather than releasing it. Some other process was needed, a process violent enough to create the heaviest elements. The process is called the process, the rapid neutron capture process. In this process, atomic nuclei are bombarded with neutrons so quickly that they capture many neutrons before they have time to undergo radioactive decay. The nuclei become enormously neutron-rich, bloated with neutrons far beyond their normal complement, and then, after the bombardment stops, they decay through a series of beta decays into the stable, heavy elements we find in nature. The process requires an environment with an extraordinary density of free neutrons, far more neutrons per cubic centimeter than exist anywhere in the universe under normal conditions. The neutron flux must be so intense that a nucleus can capture 10, 20, even 30 neutrons before it has time to undergo a single beta decay, a process that typically takes fractions of a second to minutes. This means the process must occur in an environment where the neutron density exceeds about 10 to the power of 20 per cubic centimeter and where the temperature is between 1 and 10 billion degrees. These are conditions that make the center of the sun look like a cool breeze. For decades, the leading candidate for the site of the process was core collapse supernovae, the same explosions that produce neutron stars. The idea was elegant and appealing. During the supernova, the intense neutrino flux drives neutron-rich material outward from the collapsing core, creating the conditions for rapid neutron capture. The supernova was already known to produce lighter elements, oxygen, silicon, calcium, and it seemed natural that it would also produce the heaviest ones. But when astrophysicists modeled the process in detail, running sophisticated computer simulations of the neutrino-driven wind from a freshly formed neutron star, the numbers did not work out. the material was not neutron-rich enough. The neutrinos, while driving the wind outward, also converted many of the neutrons back into protons, working against the very process they were supposed to enable. The simulations consistently produced elements up to about mass number Ia-Hendens, palladium, silver, but fell short of the heaviest R-process elements like gold, platinum, and uranium. Supernovae could produce some R-process elements, but not enough to account for the abundances we observe in the solar system, in old stars, and in the galaxy as a whole. Something was missing. Some other source, more neutron-rich, more violent, more prolific, was needed. The answer, it turned out, was neutron-star mergers. When two neutron stars orbit each other, locked in a gravitational dance by their mutual attractions, they gradually spiral inward. The existence of such binary neutron star systems is itself a testament to the resilience of these objects. Consider what it takes to produce one. Two massive stars must form in a binary system, orbiting each other. The first, more massive star evolves faster, exhausts its fuel, and explodes as a supernova, leaving behind a neutron star. The explosion is asymmetric, delivering a violent kick to the newborn neutron star. Natal kicks of hundreds of kilometers per second are common, fast enough to escape many binary systems entirely. But sometimes the binary survives. The neutron star remains bound to its companion. Millions of years later, the second star also exhausts its fuel and explodes. Another supernova, another kick. For the system to survive as a binary neutron star, it must endure two supernovae, two natal kicks, and the loss of most of the system's mass in the explosions, without the two stars being flung apart. The odds are not good. Estimates suggest that only about 1 in 100 massive binary systems survives to become a binary neutron star. They are rare, but in a galaxy with hundreds of billions of stars, rare is still enough. Einstein's general theory of relativity predicts that two massive objects orbiting each other will emit gravitational waves, ripples, in the fabric of space-time that carry energy away from the system. As energy is lost, the orbit shrinks. The neutron stars draw closer together. They orbit faster. They emit more gravitational waves. They draw closer still. It is a positive feedback loop, a spiral that can only end one way. The process is imperceptibly slow at first, taking hundreds of millions of years for the orbit to shrink significantly, but it accelerates. In the final minutes, the neutron stars are orbiting each other hundreds of times per second, approaching speeds close to the speed of light. Tidal forces begin to deform the stars. The enormous gravity of each star stretches its companion into an elongated shape, raising tides of nuclear matter kilometers high on their surfaces. The distortion grows as the stars draw closer. Matter begins to be ripped from their surfaces, forming a bridge of nuclear material between the two stars. The gravitational wave signal sweeps upward in frequency and amplitude, a cosmic chirp that grows louder and higher and faster until, finally, the two stars touch. The final few orbits happen in milliseconds. The stars are less than 50 kilometers apart, their surfaces almost brushing, orbiting each other more than 1,000 times per second. The gravitational wave signal is now at its peak frequency and amplitude, carrying energy away from the system at a rate that briefly exceeds the combined light output of every star in the observable universe. For a fraction of a second, the merging neutron stars are the single most powerful source of energy in the cosmos, not in light, not in heat, but in the vibration of space-time itself. The collision is cataclysmic. In the span of a few milliseconds, more than 2 solar masses of nuclear matter, already at densities exceeding those of an atomic nucleus, are smashed together at a significant fraction of the speed of light. The impact produces temperatures of hundreds of billions of degrees. Shock waves rip through the merging material. A fraction of the neutron star material, perhaps 1 to 10% of a solar mass, is ejected outward at velocities up to a third of the speed of light. This ejected material is extraordinarily neutron-rich. It is, after all, made of neutrons that were ripped from the surfaces of neutron stars, and in this ejected material, the reprocess ignites. Neutrons bombard the seed nuclei at an extraordinary rate. Heavy elements are forged in seconds, elements that took nature billions of years to concentrate on Earth. Gold, platinum, palladium, osmium, iridium, uranium, thorium, the entire upper end of the periodic table is created in a burst of nucleosynthesis lasting less than a minute. The newly forged elements are radioactive, violently, furiously radioactive. As they decay through chains of beta decays, alpha decays, and fission events, they release enormous amounts of energy. This energy heats the ejected material from the inside, causing it to glow. This glow is called a kilonova, a term coined by the astrophysicist Brian Metzger in 2010 because it was expected to be about 1,000 times brighter than a typical nova, though still far dimmer than a supernova. The kilonova shines in optical and infrared light for days to weeks after the merger. Its evolution follows a distinctive pattern. In the first hours and days, the glow is dominated by lighter reprocess elements, elements in the first and second peaks of the E-process abundance pattern, around mass numbers 80 and 130. These elements are relatively transparent to visible light, so the kilonova initially appears blue-white. But as the ejecta expands and cools, heavier elements, the lanthanides and actinides, with their complex electron configurations and forests of spectral absorption lines, begin to dominate the opacity. The kilonova shifts from blue to red, then deep into the infrared, as the heavy element ejecta becomes increasingly opaque to shorter wavelengths. The color change is not just a visual curiosity, it is a direct signature of the nuclear physics occurring inside the expanding debris cloud. Watching a kilonova change color is, in a very real sense, watching the periodic table being built in real time. This is not speculation. We have seen it happen. On August 2017, the LIGO and Vargo gravitational wave detectors registered a signal unlike any they had detected before. Previous gravitational wave detections had come from merging black holes, systems that produce strong gravitational waves but no light, because the merging objects have no surface and no matter to illuminate. This new signal was different. It was longer, lasting about 100 seconds as the two objects spiraled together, compared to fractions of a second for black hole mergers. The frequency sweep was characteristic of objects less massive than black holes. The signal was consistent with two neutron stars, each about 1.4 times the mass of the Sun, spiraling together and merging. The event was designated GW Diltilin 8 Diltilin Serendit, and what happened next was unprecedented in the history of astronomy. Less than 2 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short burst of gamma rays, a gamma ray burst lasting about 2 seconds, coming from the same region of sky. This was the first time a gravitational wave event had been associated with an electromagnetic signal. The gravitational wave and the gamma ray burst arrived within 1.7 seconds of each other, after traveling 130 million light-years through space. This tiny delay confirmed with extraordinary precision that gravitational waves travel at the speed of light as Einstein had predicted. Within hours, ground-based telescopes around the world, alerted by the LIGO Virgo detection, began searching the sky for an optical counterpart. They found it. A new point of light had appeared in the galaxy NGC 4993, an otherwise unremarkable elliptical galaxy about 130 million light-years away in the constellation Hydra. The new source, designated AT 2017 GFO, was the kilonova, the radioactive glow of freshly forged heavy elements produced in the merger of two neutron stars. Over the following days and weeks, more than 70 observatories on every continent and in space observed the kilonova across the entire electromagnetic spectrum, from radio waves to gamma rays. It was the most observed astronomical event in human history. Optical telescopes tracked the fading glow as it shifted from blue to red over the first week. Infrared telescopes detected the telltale signatures of heavy elements in the cooling ejecta. Radio telescopes detected the afterglow of the relativistic jet, a narrow beam of material launched along the merged object's rotation axis at nearly the speed of light, plowing into the surrounding interstellar medium and producing a slowly brightening radio signal that was still detectable months after the merger. X-ray telescopes detected emission from the same jet as it decelerated and spread. Each wavelength told a different part of the story. Each instrument contributed a different piece of the puzzle, and together they assembled the most complete picture of a cosmic cataclysm ever constructed. The observations revealed precisely what the theorists had predicted. The spectrum of the kilonova showed the unmistakable signatures of heavy elements, strontium, cesium, tellurium, and others, confirming that the air process was occurring in the merger ejecta. The amount of heavy elements produced was estimated at roughly 10 times the mass of Jupiter, including perhaps 10 Earth masses of gold and 10 Earth masses of platinum, created in a few seconds of nuclear alchemy and flung across 100 million light-years of space. Think about that for a moment. The gold in every ring, every necklace, every coin, every electronic connection on Earth, all of it was produced in events like this one. Neutron stars collided. Heavy elements were forged. The debris was scattered across space. Billions of years later, some of that debris became part of the molecular cloud that collapsed to form the Sun and the solar system. The gold settled into Earth's mantle and core during the planet's formation. Geological processes brought traces of it to the surface. Humans dug it out of the ground, and now it sits on your finger, or in a vault, or in the circuitry of the phone in your hand. Atoms that were born in the most violent collision the universe can produce, carried across billions of years and billions of miles to reach you. You are wearing the debris of a cosmic catastrophe. Every heavy element in your body, the iodine in your thyroid, the barium in your bones, the selenium in your cells, is a relic of neutron star mergers that occurred before the Sun existed. You are not just made of star stuff, as Carl Sagan famously said. You are made of neutron star collision stuff. You are made of kilonova debris. This is shocking discovery number 5, the ripples in space-time. The story of gravitational waves is, in many ways, a story about patience, about a prediction so extraordinary that it took a century to confirm, about instruments so sensitive that they can detect changes in distance smaller than a proton, and about neutron stars which provided the first proof that gravitational waves were real, decades before any detector on Earth was sensitive enough to catch them. In 1915, Albert Einstein published his general theory of relativity, a radical reimagining of gravity not as a force but as a curvature of space-time caused by mass and energy. The theory was beautiful, elegant, and profoundly strange. It said that massive objects do not pull on each other across empty space. Instead, they bend the fabric of space-time around them, and other objects move along the curves in that fabric. The sun does not pull the earth toward it. The sun bends the space-time around it, and the earth rolls along the resulting curve. Gravity is not a force, it is geometry. One of the theory's more exotic predictions was that accelerating masses would produce ripples in space-time, gravitational waves, that would propagate outward at the speed of light, stretching and squeezing space as they passed. These waves would be transverse, oscillating perpendicular to their direction of travel, and quadrupolar, meaning they would stretch space in one direction while compressing it in the perpendicular direction, then reverse, oscillating back and forth as the wave passed. Einstein himself was skeptical that gravitational waves would ever be detected. He wavered on whether they were even real. At one point, he wrote a paper arguing that gravitational waves did not exist, only to withdraw it before publication when a referee pointed out an error in his calculations. The effect was extraordinarily weak. Even the most violent events in the universe, supernovae, black hole mergers, neutron-star collisions, would produce gravitational waves that, by the time they reached Earth, would stretch or compress distances by less than the width of a proton. Detecting such a signal seemed impossible. Not just difficult, but genuinely, fundamentally beyond the reach of any conceivable technology. The first indirect evidence came from neutron stars. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other, one of which was a pulsar whose regular radio pulses served as an exquisitely precise clock. By timing the pulsar signals over years, Hulse and Taylor could track the orbit with extraordinary precision. They found that the orbit was shrinking. The two neutron stars were spiraling together at a rate of about 3.5 meters per year, exactly as general relativity predicted for a system losing energy through gravitational wave emission. The orbit was shrinking because gravitational waves were carrying energy away from the system. The match between the observed orbital decay and Einstein's prediction was precise to better than 1%, a stunning confirmation of general relativity and the first proof that gravitational waves existed. Hulse and Taylor were awarded the 1993 Nobel Prize in Physics for this discovery. But the gravitational waves themselves had not been directly detected. That would require another 2 decades of technological development, the construction of the most sensitive measuring instruments ever built. LIGO, the Laser Interferometer Gravitational Wave Observatory, consists of 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana. Each detector is an L-shaped interferometer with arms 4 kilometers long. A laser beam is split and sent down both arms, bouncing off mirrors at the far ends and recombining at the vertex. When a gravitational wave passes, it stretches one arm and compresses the other by a minuscule amount, typically about 1/10,000th the diameter of a proton, producing a detectable change in the interference pattern of the recombining laser beams. Their sensitivity is almost incomprehensible. LIGO can detect changes in the length of its 4-kilometer arms that are smaller than 1/10,000th the width of a proton, a distance of about 10 to the minus 19 meters. To appreciate what this means, imagine stretching LIGO's arm to the distance of the nearest star, about 4 light-years. At LIGO sensitivity, the instrument would need to detect a change in that distance smaller than the width of a human hair. To achieve this extraordinary sensitivity, the mirrors must be isolated from every conceivable source of vibration, seismic activity, traffic on nearby roads, ocean waves crashing on distant coastlines, wind buffeting the buildings, and even the quantum fluctuations of the laser light itself. The 40-kilogram mirrors, exquisitely polished fused silica, among the smoothest objects ever manufactured, hang from quadruple pendulum systems inside the largest vacuum chambers in the world. The vacuum inside the beam tubes is better than the vacuum of outer space, about a trillionth of atmospheric pressure, because even individual air molecules bouncing off the laser beam would introduce intolerable noise. The laser operates at 200 watts and extraordinary stability, its frequency locked to a reference cavity with precision measured in parts per quintillion. Seismometers monitor ground motion continuously, and active feedback systems adjust the mirror positions thousands of times per second to compensate. The entire system pushes against the fundamental limits imposed by quantum mechanics, and in recent upgrades, LIGO has begun using squeezed light, a quantum mechanical technique that reduces the quantum noise in the laser below the standard quantum limit, wringing even more sensitivity out of the instrument. On September 13th, 2015, LIGO detected gravitational waves for the first time. A signal from 2 black holes, each about 30 times the mass of the Sun, spiraling together and merging approximately 1.3 billion light-years away. The detection was announced in February 2016 and led to the 2017 Nobel Prize in Physics for Rainer Weiss, Kip Thorne, and Barry Barish. But it was the detection of GW 17087, the neutron star merger, 2 years later, that truly demonstrated the power of gravitational wave astronomy. Because neutron stars have surfaces and matter, their merger produced not just gravitational waves, but light, electromagnetic radiation across the entire spectrum. For the first time, astronomers could study a cosmic event using both gravitational waves and traditional telescopes simultaneously. This was the dawn of multi-messenger astronomy, a new way of observing the universe that combines fundamentally different types of signals to create a more complete picture than either could provide alone. The LIGO-Virgo collaboration has continued to improve its sensitivity. The current 4th observing run, O4, which began in 2023, has already detected hundreds of gravitational wave events, including additional neutron star mergers and the first detections of objects in the mass gap between the heaviest neutron stars and the lightest black holes. By August 2025, LIGO had surpassed 200 detections in O4 alone, and in August 2026, the updated JWTC 4.0 gravitational wave catalog was released, providing the most comprehensive survey of compact object mergers ever compiled. Each detection adds to our understanding. The masses, spins, and orbital parameters of merging neutron stars constrain the equation of state, telling us about the interior structure of these objects. The gravitational wave signal from a neutron star merger encodes information about how the star deforms under tidal forces in the moments before contact. A stiffer equation of state, meaning the neutron star resists storm compression more, produces a larger tidal deformation and a different gravitational wave signal than a softer equation of state. By analyzing these signals, physicists can determine whether neutron stars are fluffy or compact, and by extension, what kind of matter exists in their cores. Gravitational wave astronomy has also provided a new way to measure the expansion rate of the universe. The gravitational wave signal from a neutron star merger gives a direct measurement of the distance to the source, independent of the traditional distance ladder used in optical astronomy. Combined with the redshift of the host galaxy, this provides an independent measurement of the Hubble constant. The measurement from GW 117H1 was not precise enough to resolve the Hubble tension, the discrepancy between different measurements of the expansion rate, but future detections, as LIGO and its partner detectors become more sensitive, will provide increasingly precise measurements that may help solve one of the biggest puzzles in cosmology. The future of gravitational wave astronomy is extraordinary. Next-generation detectors. The Einstein telescope in Europe and Cosmic Explorer in the United States are being planned with sensitivities 10 times greater than current LIGO. These detectors will be able to detect neutron star mergers across the entire observable universe, providing a complete census of these events and their contribution to the production of heavy elements. And in space, the LISA mission, the Laser Interferometer Space Antenna, will detect gravitational waves at frequencies too low for ground-based detectors, opening an entirely new window on the gravitational wave universe. Neutron stars provided the first evidence for gravitational waves. They provided the first multi-messenger gravitational wave detection, and they will continue to be among the most important sources for gravitational wave observatories for decades to come. In a very real sense, neutron stars are the Rosetta Stone of gravitational wave astronomy, the objects that translate between the language of gravity and the language of light. This is shocking discovery number 6, the star that should not spin that fast. We have already mentioned that neutron stars can spin at extraordinary rates, hundreds of times per second, but we have not yet explored just how strange and how violent the processes are that create these ultra-rapid rotators, or what their existence tells us about the limits of matter. Consider what it means for an object 20 kilometers across to rotate 716 times per second. The equatorial surface of PSR J1748-2446 ED is moving at approximately 70,000 kilometers per second, 24% of the speed of light. At this speed, the neutron star is on the verge of breaking apart. The centrifugal force at the equator, trying to fling matter outward, is balanced against the gravitational force, pulling matter inward. If the star were spinning just a little bit faster, the centrifugal force would exceed gravity, and the star would shed material from its equator or, in extreme cases, simply fly apart. This near breakup spin rate places a fundamental constraint on the nature of neutron star matter. If the interior were made of something soft and easily deformed, like a fluid with low viscosity, the star would bulge dramatically at the equator and break apart at lower spin rates. The fact that neutron stars can spin as fast as they do without breaking apart tells us that the matter inside them is extraordinarily stiff and resistant to deformation. This observation alone rules out certain proposed equations of state, theoretical models of neutron star matter that predict a material too soft to withstand these rotational stresses. But how does a neutron star get spun up to such extreme rates in the first place? The answer involves one of the most dramatic partnerships in astrophysics, a relationship between a neutron star and a companion star that can last billions of years and transforms both objects beyond recognition. Millisecond pulsars, the fastest spinning neutron stars, are almost always found in binary systems. Their histories follow a common pattern. A neutron star born in a supernova explosion billions of years ago, initially spins rapidly but gradually slows down over millions of years as it loses rotational energy through electromagnetic radiation. Eventually, it becomes a slow, dim, unremarkable neutron star, essentially retired. But if the neutron star has a companion star, a normal star orbiting nearby, the story does not end there. As the companion evolves and expands, it may fill its Roche lobe, the gravitational boundary beyond which material is no longer bound to the companion, but instead falls toward the neutron star. Gas from the companion streams across the gap between the two stars, forming a swirling accretion disk around the neutron star. As the gas spirals inward through the disk and lands on the neutron star's surface, it transfers angular momentum, spinning the neutron star up. Over millions of years of accretion, the neutron star can be spun from near-death slowness back up to rotational periods of just a few milliseconds. The process is called recycling, an evocative term that captures the essence of what is happening. The neutron star is recycled from a slow, dead pulsar into a fast, bright millisecond pulsar. It is a resurrection of sorts, a dead star brought back to life by the sacrifice of its companion, spinning again, beaming again, detectable again from across the galaxy. The companion star, meanwhile, is slowly consumed. The neutron star's gravity strips away its outer layers, reducing it to a white dwarf, or, in the case of the Black Widow pulsars, evaporating it entirely. The neutron star takes everything the companion has to offer: its mass, its angular momentum, its very substance, and transforms itself into one of the most extreme objects in the universe. The accretion process also heats the neutron star's surface to temperatures of millions of degrees, producing X-ray emission that can be detected by space-based X-ray telescopes. Many millisecond pulsars were first discovered as X-ray sources before their pulsations were detected at radio wavelengths. The transition from an accreting X-ray source to a radio millisecond pulsars, the moment when accretion stops and the neutron star's radio beams switch on, has been observed directly in a few systems, providing a real-time view of the recycling process. There is something particularly remarkable about the timing precision of millisecond pulsars. Because they spin so fast and so steadily, they serve as extraordinarily precise clocks, natural timekeepers that rival the best human-made atomic clocks. This precision has been exploited for one of the most ambitious experiments in all of astrophysics, the pulsar timing array. A pulsar timing array monitors the arrival times of radio pulses from dozens of millisecond pulsars distributed across the sky. If a gravitational wave passes through the galaxy, it will slightly alter the distance between Earth and each pulsar, causing tiny, correlated changes in the arrival times of the pulses. By monitoring many pulsars simultaneously and looking for correlated timing residuals, tiny deviations from the expected arrival times that show a specific spatial pattern, astronomers can detect gravitational waves at frequencies far too low for LIGO to observe. In 2023, several pulsar timing array collaborations around the world, Nanograv in North America, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array in Australia, simultaneously announced strong evidence for a low-frequency gravitational wave background. This signal is thought to be the combined hum of millions of supermassive black hole binaries across the universe, pairs of enormous black holes slowly spiraling toward merger in the centers of galaxies. The detection opened yet another window on the gravitational wave universe, a window that is fundamentally different from LIGO's and that was made possible entirely by the extraordinary precision of neutron stars as cosmic clocks. Neutron stars are not just interesting objects to study. They are instruments, tools for exploring the universe in ways that no human-made device can replicate. They are clocks that can detect gravitational waves no terrestrial detector can reach. They are laboratories where physics operates under conditions we cannot create on Earth. They are beacons that mark their positions with a precision that could guide spacecraft across interstellar distances, a technology called XNAV, X-ray pulsar navigation, which has already been tested in orbit and may someday help humanity navigate beyond the solar system. The same cosmic lighthouses that Jocelyn Bell found by accident in 1967 could one day serve as the GPS satellites of interstellar travel. This is shocking discovery number 7. The space between life and death. There is a boundary, sharp, absolute, and unforgiving, that separates neutron stars from black holes. It is called the Tolman-Oppenheimer-Volkoff limit, and it represents the maximum mass that a neutron star can support before it collapses under its own gravity into a black hole. The exact value of this limit depends on the equation of state, the same mysterious relationship between pressure and density that governs the interior structure of neutron stars. Current estimates place the limit somewhere between about 2 and 2.5 solar masses, with most calculations converging around 2.2 solar masses. Below this limit, neutron degeneracy pressure and the repulsive nuclear force can hold the star up against gravity. Above it, nothing can prevent collapse. The neutron star implodes, its surface vanishes behind an event horizon, and a black hole is born. This limit is not just a number. It is a frontier, a boundary between two fundamentally different types of objects, separated by a margin of mass so narrow that nature seems to flirt with it constantly. We have observed neutron stars with masses very close to the limit. The most massive confirmed neutron star, PSR J0740 PS60620, has a mass of about 2.08 solar masses, and we have observed black holes with masses just above the limit. Between them lies a zone of uncertainty, the so-called mass gap, where we are not sure whether an object should be a neutron star or a black hole. The mass gap has been one of the enduring mysteries of compact object physics. For years, observations of X-ray binary systems, neutron stars, and black holes orbiting normal companion stars, with mass estimates derived from the orbital dynamics, suggested a curious absence of objects between about 2 and 5 solar masses. Neutron stars clustered around 1.4 solar masses. Black holes seemed to start at about 5 solar masses. Between them, nothing. A gap. A desert on the mass spectrum where compact objects apparently did not exist. Was this gap real? A consequence of the physics of supernovae, which might preferentially produce either light neutron stars or heavy black holes, but nothing in between. Some models of core collapse supernovae suggested exactly this, that the explosion mechanism naturally divided the outcomes into two populations with a gap in the middle. Others proposed that the gap was a consequence of how black holes form. That fallback of material during the supernova might push the remnant from neutron star masses directly up to several solar masses, skipping the intermediate range entirely. Or was the gap an observational artifact, a result of the difficulty of detecting objects in this mass range? Objects in the mass gap might not shine brightly in X-rays, or might exist in systems where their masses are difficult to measure. Perhaps they were there all along, hiding in plain sight. Gravitational wave astronomy is beginning to answer this question. In ET 724, LIGO detected GW Tusi Sentanused Tandifobutandi, a gravitational wave signal from the merger of a neutron star with a compact object of about 3.6 solar masses. This object sits squarely in the mass gap, too heavy to be a conventional neutron star, too light to be a typical black hole formed from stellar collapse. What is it? A very heavy neutron star supported by exotic matter in its core? A very light black hole formed through an unusual channel? Or something entirely new? An object that does not fit neatly into either category. The mass gap is not merely a taxonomic curiosity. It probes the most fundamental physics of matter and gravity. If the maximum mass of a neutron star is low, around 2 solar masses, then the equation of state is soft, meaning the matter inside is easily compressed and the core is dense enough to contain quark matter. If the maximum mass is higher, around 2.5 solar masses, the equation of state is stiff, meaning the matter resists compression and exotic phases may not be present. Every detection of a compact object near the mass gap narrows the possibilities and brings us closer to understanding what happens to matter when it is pushed to the absolute limit. And when a neutron star does cross the limit, when it accretes too much material from a companion, or when 2 neutron stars merge and their combined mass exceeds the maximum, the collapse to a black hole is essentially instantaneous. The entire structure of the neutron star, its crust, its pasta layers, its superfluid core, falls inward at close to the speed of light. A horizon forms, the surface, the matter, the identity of the neutron star disappears behind a boundary from which nothing can return. In some neutron star mergers, the combined mass is just barely above the limit. In these cases, the merged object may survive briefly as a hypermassive neutron star, supported temporarily by rapid differential rotation and thermal pressure, before these temporary supports dissipate and the object collapses to a black hole. This brief intermediate stage, lasting perhaps milliseconds to seconds, may produce distinctive gravitational wave and electromagnetic signals that future detectors could observe. Catching a neutron star in the act of becoming a black hole, watching the transition from matter to singularity in real time, would be one of the most extraordinary observations in the history of physics. The Tolman-Oppenheimer-Volkoff limit is, in a sense, the universe's last line of defense for matter. Below it, matter can exist, compressed, deformed, exotic, but still recognizably material. Above it, matter loses, gravity wins. And everything that makes a neutron star, its surface, its magnetism, its spin, its identity, is erased. There is a philosophical depth to this boundary that deserves a moment of reflection. A neutron star exists at the razor's edge between being and nothingness. It is the most compressed form of matter that the universe permits, the densest thing that can still be called a thing. One more solar mass, one more teaspoon of accreted material, and it crosses the threshold. The surface vanishes. The information about what it was, its composition, its temperature, its magnetic field, becomes inaccessible, locked behind an event horizon. The neutron star does not just die. It ceases to be an object in any meaningful sense. It becomes a region of space-time from which nothing can return. And yet, even in this final act, neutron stars give us something. The gravitational waves emitted during the collapse carry information about the equation of state, about what the matter was doing in its final moments before the horizon formed. The brief flash of electromagnetic radiation, if any escapes, tells us about the magnetic field and the surface conditions at the instant of transition. Even in their death, neutron stars are telling us about the nature of matter and gravity. They are, to the very end, the most generous laboratories in the cosmos. The boundary between neutron stars and black holes is not merely a line on a mass diagram. It is the boundary between two fundamentally different descriptions of reality, between objects governed by the physics of matter and objects governed by the geometry of space-time alone. Neutron stars live on the matter side. Black holes live on the geometry side. And the boundary between them is where our understanding of both runs out. Let us step back now and consider what we have learned tonight. Neutron stars are born in violence, forged in the collapse of massive stars, born in supernovae that briefly outshine entire galaxies. They are the densest objects with a surface, spheres of nuclear matter 20 kilometers across, containing more mass than the Sun, with densities that exceed anything in the terrestrial universe by factors of trillions. Their interiors contain matter in states so exotic that they push the boundaries of physics, superfluid neutrons, nuclear pasta, and possibly quark matter or strange matter that has not existed freely since the first moments after the Big Bang. They spin at extraordinary rates, up to hundreds of times per second, and serve as the most precise natural clocks in the universe. They produce magnetic fields a quadrillion times stronger than Earth's, capable of disrupting entire planetary atmospheres from across the galaxy. They collide and forge the heaviest elements in the periodic table, the gold, platinum, and uranium that we find on Earth, created in seconds of nuclear alchemy during events so violent that they send ripples through the fabric of space-time. They provided the first evidence for gravitational waves. They provided the first multi-messenger astronomical observation. They may be the source of the mysterious fast radio bursts that flash across the cosmos. And they sit on the boundary between matter and oblivion, the narrowest possible margin separating a neutron star from a black hole. There is a moment just after a supernova, when the neutron star first forms, when the core has just bounced, when the neutrinos are still flooding outward, when the shock wave is still tearing through the outer layers of the dying star. In that moment, the neutron star is hotter than anything in the universe, hundreds of billions of degrees, hotter than the center of the Sun by a factor of 1,000. It is spinning rapidly, glowing in neutrinos and gravitational waves, surrounded by the expanding debris of its own birth. And then it cools. Over seconds, then minutes, then hours, the temperature drops. The crust begins to crystallize. The superfluid forms in the interior. The magnetic field settles into its configuration. The rotation begins its long, slow decline. The neutron star becomes what it will be for billions of years, a dense, spinning, magnetic remnant, gradually fading, gradually slowing, gradually cooling toward the background temperature of the universe. Most neutron stars will outlast the stars that bore them. They will outlast the galaxies that contain them, long after the last normal star has burned out. Trillions of years from now, in the cold, dark future of the universe, neutron stars will still be there. Dark, cold, silent, slowly cooling toward absolute zero, spinning ever more slowly, their magnetic fields gradually decaying, their crusts gradually settling. How slowly? The time scales are staggering. A neutron star born today, in the current epoch of the universe, will still be detectably warm, in X-rays at least, in 1,000,000 years. In 1,000,000,000 years, it will have cooled to temperatures of a few thousand degrees, warm by human standards, but cold by neutron star standards, and too faint to detect with current instruments. In 100 billion years, when the last red dwarf stars in the galaxy are finally sputtering out, the neutron star will have cooled to a few degrees above absolute zero, its surface temperature approaching the cosmic microwave background radiation that bathes the universe. But the neutron star will still be there. Its crystal lattice crust will be intact. Its superfluid interior will still flow without friction. Its angular momentum, slowly bleeding away over eons, will still turn it, imperceptibly slowly, perhaps once every few years, then once every century, then once every millennium. A lighthouse whose beam has faded to nothing, spinning in silence in the dark. They will be among the last structured objects in the universe, relics of an era when stars burned and galaxies shone and the cosmos was full of light. In the degenerate era, when the universe is 100 trillion years old and the less conventional star has exhausted its fuel, neutron stars will remain alongside white dwarfs and black holes as the only surviving remnants of the stelliferous age. In the unimaginable far future, when the universe has expanded beyond all recognition and the last photons have redshifted into oblivion, neutron stars will sit in the darkness like monuments, tombstones marking the places where massive stars once lived and died and scattered their ashes across the void. Eventually, even the neutron stars may not endure forever. If protons decay, a possibility predicted by some grand unified theories of particle physics with a half-life of perhaps 10 to the power of 40 years, then the neutrons inside neutron stars, which can decay into protons, will eventually disintegrate as well. Over timescales that dwarf the current age of the universe by a factor of 10 to the power of 30, the neutron star would slowly, imperceptibly dissolve, its matter converting to energy, photon by photon, over eons so vast that the current age of the universe is less than the blink of an eye in comparison. But this is speculation at the farthest reaches of theoretical physics, and for all practical purposes, for any timescale that has meaning in the context of the universe as we know it, neutron stars are forever. There is something beautiful in this, something that goes beyond physics and touches on something deeper. These objects, born in catastrophe, forged in violence, existing at the very edge of what matter can withstand, are also among the most enduring things the universe will ever produce. They are tough, they are resilient, they survive. Think of what a neutron star has endured. It began as hydrogen, the simplest element, the first atom, forged in the Big Bang 13.8 billion years ago. That hydrogen collapsed into a molecular cloud, condensed into a protostar, ignited nuclear fusion, and burned as a massive star for millions of years, transforming itself through every element on the periodic table, from hydrogen through helium, carbon, neon, oxygen, silicon, and finally iron. Then it died, catastrophically, violently, in a supernova that outshone a galaxy. Its core was crushed to nuclear density in less than a second. It was born again as something entirely new. Neither a star nor a planet, neither solid nor liquid nor gas, but something else, something that exists only at the boundary of what physics allows. And it survived. It survived the supernova. It survived the natal kick that sent it hurtling through space at hundreds of kilometers per second. It survived the intense heat of its birth, cooling gradually over millions of years. It survived the slow decay of its magnetic field, the gradual loss of its rotational energy, the tidal interactions with companion stars, the occasional starquake that cracked its crust and rearranged its interior. It will survive the death of the sun. It will survive the dissolution of the Milky Way. It will survive into the deep future of the universe, into eras so remote that they have no names, only numbers. Even when the universe itself winds down and the lights go out, neutron stars will remain, carrying within their frozen cores a memory of the nuclear fire that created them, a record of the elements they forged, a testament to the physics that governs everything from the smallest quark to the largest structure in the cosmos. And the elements they created, the gold and platinum and uranium scattered by their collisions, those elements became part of new stars, new planets, new worlds. They became part of the molecular clouds that coalesced into solar systems. They became part of the Earth. They became part of you. The iron in your blood, every atom of it, was forged in the core of a massive star, built nucleus by nucleus in the silicon-burning shell of a supergiant in the last day of its life. The calcium in your bones was assembled in the oxygen-burning layers of a star that died before the sun was born. The carbon in your DNA was fused from helium in the triple alpha process inside a red giant, a reaction so improbable that it relies on a quantum resonance that the astrophysicist Fred Hoyle predicted must exist simply because we are here to ask the question. But the iodine in your thyroid, the selenium in your cells, the gold in the ground beneath your feet, those came from the collision of neutron stars, from the merger of two impossibly dense objects spiraling toward each other over millions of years, finally touching, finally shattering the boundaries of nuclear physics, finally scattering their contents across 100 million light-years of space. You are not just made of stardust. You are made of the debris of the most violent events the universe can produce. You carry within your body atoms that were forged in the last millisecond before two neutron stars became one. Atoms that were born in a flash of gravitational waves and gamma rays and kilonova light scattered across the cosmos, gathered by gravity into clouds, compressed into planets, and assembled over billions of years into a creature that can look up at the stars and wonder where it came from. Now you know. So let tonight be gentle. Let the numbers settle, the 6 billion tons per teaspoon, the 716 rotations per second, the quadrillion Tesla magnetic fields, the 100 billion degree birth temperatures. You do not need to hold them all. They are just signposts pointing towards something larger, something that connects the smallest particle in an atomic nucleus to the largest structure in the cosmos. Neutron stars are the universe at its most extreme. And at its most extreme, the universe is not cruel. It is not indifferent. It is simply vast and ancient and patient and full of processes that produce over billions of years everything that exists, including you, including the atoms in your hands, including the curiosity that made you stay and listen this far. The universe does not owe us an explanation, but it gives us one anyway, written in gravitational waves and gamma rays, in the precise ticking of pulsars and the slow glow of kilonovae, in the impossible density of nuclear matter and the patient spiral of two dead stars falling toward each other across the darkness. We started tonight with a question. What are the most terrifying objects in the universe? We have found our answer. They are also the most beautiful, the most generous, the most enduring. Neutron stars, born in fire, forged in collapse, spinning in silence, scattering the elements of life across the cosmos. All you have to do is listen. And the universe, it turns out, has been speaking all along, in pulses and flares and ripples and light from objects so dense and so strange and so beautiful that they remind us again and again that the cosmos is not something we observe from the outside, it is something we are part of, something we are made of, something that made us and will outlast us and does not care that we are small, because even the smallest things in this universe are made of miracles. The neutron stars are spinning in the darkness tonight. They have been spinning since before the Earth existed. They will be spinning long after the sun goes dark. And somewhere in the space between two of them, the elements of a future world are being forged, scattered like seeds across the void, waiting for gravity to gather them, waiting for chemistry to assemble them, waiting for something curious and brave and impossibly unlikely to look up at the sky and ask the oldest question: what are we made of? Now you know the answer. You are made of neutron stars.